Hi, I'm Randall Heyman, a mathematics academic. Many students will find their learning impacted by the coronavirus outbreak. So I'm using my YouTube channel to make quick turnaround videos covering mathematical problems and concepts. So if you're a lecturer, tutor, high school or primary school teacher, parent, grandparent or student, and you would like me to make a video, use the comment section below the video. So Benny Lowe contacted me. He's from Fremont, California. And he's been watching with his class, some of the videos I've been doing on abstract algebra. And he's asked me if I could go through this problem here. If D is an integral domain, then dx is also an integral domain. He contacted me by by email actually. So if you want to email me, there's an email address, coronahelpmathematics@gmail.com. But just as easy and nice to put a comment below the video. Okay, so let's just revise a couple of things from previous videos. An integral domain is a commutative ring with a multiplicative unit and no zero divisors. So there are three major differences between an integral domain and a ring, which I've just covered. We also saw in a previous video that if R is a ring, then the ring of polynomials, which we represent with Rx, is also a ring. Okay, so what we need to show is this. If D is an integral domain, then dx is also an integral domain. So just let's make a few comments first. So dx is equal to, well, we really should do it like this. It's the set of A0 plus A1x plus dot, dot, dot. And AI is an element of, let's draw that properly. AI is an element of the domain D, and M, let me write it here. Whoops. And running out of room here, aren't I? M is an element, it's a positive integer, so well, it could be 0. So better do it that way, I suppose. So that's the set, and then we're using normal polynomial addition and multiplication. Okay, so there's that. I'll represent the polynomial slightly differently when we get into it, I think, but that'll do to start us off. So that's what dx is. Now, so what's my plan here? So my plan is to say sort of one is that, I'll do a proper proof in a sec, but this is just a plan. So my idea is, so what is my plan? Oh yeah, if D is an integral domain, D is I'll just put ID, integral domain. Well, that implies that D is a ring. And that implies that, what are we saying? D is a ring. So that implies, yeah, that's right, that dx is a ring. So if D is a ring, all the polynomials with D as coefficients is also a ring. We've already discussed that. And then what I'll have to do is it'll suffice to show that all I've got to show is the extra 3 things. Now so I've shown dx is a ring. Now I've just got to show that dx is commutative. We better also show that it has a multiplicative unit. Remember, that's just a number like 1, that when you multiply by a polynomial, you get the same polynomial. So we'll be using the polynomial 1 to do that. And D is commutative, has a multiplicative unit, and has no zero divisors. Okay, and so once we've done that, then it's just a question of showing that it's commutative, has the multiplicative unit, and no zero divisors. So there'll be 3 sections to that, and then we'll be done. Okay, so let's start. And I don't want to make this too long. I might break it into two videos, I think. Proof. Okay, so what did we say? We said we have to show, so if D is an integral domain, then D is a ring. So I've said this previously. Generally, if you're in this situation, somewhere in your lecture notes, you will have been told that what I've just written is correct. So you don't have to prove that, but you'll have to use your judgment. Maybe in some cases you might have to, but generally you won't have to. You just state it as a fact. You might have to put bracket from the lecture notes, whatever your instructor requires is what you'll do. So if D is an integral domain, then D is a ring. And so dx is also a ring. Good. So once again, that's just a statement we can make because it was in the notes before. Okay. So now I would just say it will suffice to show that dx is commutative has a multiplicative unit and has no, let's lift this up a bit, has no zero divisors. Yeah, I think it's going to suit me to do this in 2 videos. I'll do some of what we need to do, and then I'll stop and we'll do it in the second video. We'll finish it off. So commutativity is what we need to show. Now, in the past, so what we will do, actually, let's write this out. Suppose f and g are elements of dx. So f and g are polynomials where the coefficients are elements of this integral domain D. So what I would normally write is, or maybe I'd even write let fx. Now, what I'd normally do is I'd do this. I'd say what I did in previous videos. I went like this: a1x1 plus amxm, where all the AIs are elements of D and where m is a positive integer. I think what I'm going to do is I'm going to write it like this instead. So this keeps going, but I'll say here that AI is an element of D for all I. I'll also say that AI is equal to 0 for all I greater than m. So I'm saying this polynomial goes on forever, if you like, but all of these here have past m have a coefficient of equal to 0. So it's exactly the same polynomial. It will just suit me better, I think, in the way I set things out. So this is the sort of thing that comes with a bit more experience. And here, of course, if I was going to be m is an element of, it's a positive integer, could be 0 as well, I suppose. Okay, and let's let gx equal b0 plus B1x1. And this time it'll just go up to Bn actually. It's a different polynomial, so it might have a different degree. So we'll make this Bnxn plus ... where Bi is every element, well, every Bi is an element of the integer domain for all I. Bi is equal to 0 for all I greater than n this time, and we'll make n an element of z plus the integers, positive integers, yeah, including and 0. Okay, so that's good. Now what we can do is then, now keep in mind what we've got to try and do here. We have to show that fx plus gx equals gx plus fx. So I suppose we could write fx plus gx is equal to actually I will write this first line just so you get the hang of it. A0 plus B0 plus A1 plus B1 x to the 1 plus, and then that just goes on. So I'll write it actually in this way, I think, equals I equals 0 to infinity AI plus BI x to the I. And now, remember these AI and BIs we've said are just elements of the integral domain. An integral domain is commutative, so I can swap them around. And you might want to just put here, since AI and BI are elements of D for and hence commutative. I think that'd be okay. Just explaining why we swapped them around. And if you wanted now, I suppose you could split this up into two summations. And now, of course, that just equals g of x plus f of x. And so what we've shown is, so dx is commutative. So I'll show you here, I'll just drop this down a little bit. So you can see up here we started off with fx plus gx, we ended up with gx plus fx, and the two are equal, so dx is commutative. So let's leave it there and I'll finish it off on the next video.